All right. So we're going to go through the last kind of type of example. Well, I guess technically we have two more, but the last two population example that we have, which is when we look at the difference between sample means, but we aren't given these known population variances. All we have are sample variances. So just like with one population, if we only have sample variances, that means we're going to have to use that student t distribution. Okay? So everything's going to be set up pretty much exactly the same as the types of examples that we worked through last week, where we had the difference in sample means. But now, instead of population variances that are known, we're going to have to only use sample variances, which result in us not looking up a z value that gives us alpha over 2 on either side of our confidence interval, but we need a t value that gives us alpha over 2 on either side of that confidence interval. Okay? So how many degrees of, so usually our degrees of freedom before was just n minus 1, right? We had one population. The problem is we have two populations. So why don't I just do, like n minus 2, right? I've got two samples, take both sample sizes, subtract 1. So you can do that. You've got the exact same sample sizes. Now, more often than not, we won't have the same sample size from each group. And so the reason why the degrees of freedom becomes a little more complicated is because, well, one group might have a degrees of freedom of 49, the other has one of 36. Well, those are two completely different student t distributions. When we go to look at the difference in sample means, we have to look it up on one student t distribution. So do I do like some sort of weighted mean between the two? And the answer is kind of, right? So remember, this guy here represented the standard deviation for the difference in our sample means. Each one of these represented the variance of each population's sample mean. So what we're going to do is we're going to use those variances and come up with some sort of kind of weighted average of the two. So our degrees of freedom, for now it's called delta. So yeah, how many degrees of freedom? All of them. It's going to look something like this, right? This is nasty. Don't worry about writing this down because it's very easy to make a mistake using this. Now, if we went ahead and calculated this ahead of time, then we'd have like small numbers. We could break this down into parts. But I'm not as interested as you being able to use this equation because it's just going to help us identify what student t distribution do we need to use. And so what I've done is I either will give you an assume, like I'll tell you to assume the degrees of freedom is this, if I'm on the exam or a problem, and even on the Connect homework, if you have ones where you need to use the degrees of freedom, I'll get a Canvas announcement up there that identifies which of those problems, I guess I'll be telling you which problems you should be using the student t for, but I'll give you the degrees of freedom for each one. Or there may be one where like you have to use this formula one time, but I'm not going to expect that you use this on the exam or even on the Excel assignment, which got pulled open here. Notice there's some weird things when you download this on this enrollment 2 file. So I believe this is the second question. But if you find the sample mean, variance, and sample size for male and female undergraduates here, once you fill these values in, so I'll just make some things up here. Notice it automatically calculates that degrees of freedom for you because I already have that function entered into Excel. That you can kind of see how with all the this is very easy to make a mistake. So I didn't want it to be kind of you have to get penalized for this somewhat complicated formula. It's already built into this Excel document for you. So as long as you calculate these things in the, kind of how I have this formatted in these 6 cells, it should update this degrees of freedom and calculate it for you. Now notice here it would be a degrees of freedom of 4.7. Well, our degrees of freedom has to be an integer. If we look at that student t table, it's 1, 2, 3, 4, like those row headings, all integer values. So we'll always do what I call floor it because that's the name of the function in Excel. But basically it's rounding down no matter what your decimal is. So notice here 4.7 still becomes 4, right? We never round up, we're always pushing it down, right? Or flooring it. Those aren't the actual values though, but once you plug them in, should kind of calculate that for you in Excel. So we've got our degrees of freedom. The way we build confidence intervals is going to be exactly the same. Right? We identify the pieces of information we're given, sample means, variances, sample sizes. What level of confidence interval do we want to build? Alpha. Look up that t-value that gives us alpha over 2 on either side of our interval using this degrees of freedom. Once again, you guys can kind of punt on this part. I'll always be giving that to you. So once we have that t-value, it's just a matter of plugging everything in. Our confidence interval equation looks exactly like what we were doing before. It's just that instead of population variances, we have sample variances and a t-value instead of a z-value. But both of them still represent the number of standard deviations the way we need to go to build our upper and our lower bound. Okay. So let's look at an example. So here, I'm going to write out my confidence interval equation in the context of our example, and we'll think about plugging our values in. So my group 1, I think the setup was I had the response time for people who were texting while driving versus those who were not. Right? So I'm going to take the non-texters response time, sample mean response time, subtract the texters response time. This kind of represents that sample difference I'm going to find. And then going to go a certain number of standard deviations away that gives me alpha over 2, right? Or this t-value that gives me alpha over 2 on either side of my interval. And then multiply that by the standard deviation of the statistic that I'm interested in, which is the difference in sample means. It's just that now I'm going to write this as an S instead of sigma because I'm using not known population variances from each group to calculate this, but only sample variances. I wrote group 1 and group 2, sorry. So this is non-texters. I guess this would be my texters. So at this point, it's just going to be a matter of plugging in the values that I was given, right? So if I leave this open here, we found what? Non-texters response time, there was 1.3. People who were texting, their average response time was 2.36. We don't have the t-value, we haven't looked that up yet. The variance for the non-texters was 0.16. Sample size was 49 of them. And then my texters variance was 1.44, and I had 64 of them. So all I'm doing here is just plugging in the values I was given. The last thing I need to do is find this t-value such that I have alpha over 2 on either side of this interval. Right? My alpha is, if I have a 90% confidence interval, alpha should be what? 90% confidence interval, alpha would be, 0.1. Divide that by 2. So the area that I want in that tail is 0.05. And I think I'm told, or at least I'm showing you here, I've got this degrees of freedom. So it calculates out to be 80.39. We push it down to the next nearest integer. So we've got a degrees of freedom of 80. So we're going to look up this area that we want in the tail at a degrees of freedom of 80 on my student t table. So 0.05 was that area that I want in the tail. I'll scroll down to my degrees of freedom of 80, 1.664. Right? And now it's just a matter of computation, getting this entered in my calculator. Subtracting this margin of error to my lower bound, adding it to my upper bound. Now notice, I could calculate this ahead of time and then just have one number to plug in. And we'll look at an example in Excel here in a second. That's kind of how I'll have it set up. Some other things that we could point out. I didn't give you any examples or answers here, like multiple choice, but if I had, you know that the sample difference that you're centering your confidence interval around here would be -1.06. So this should be smack dab in the middle of our confidence interval. Other than that, it's just a matter of getting this plugged in. So if I do, let me see here. There we go. So if I do that, I get negative 1.33 and negative 0.76. Okay. So how do we use this to make some interesting statements? So negative 1.33, negative 0.79. Well, remember, we had this set up as non-texters minus the texters. So if I only have negative values in my confidence interval, at the 90% level, what could I say is true about the response time, average response times for texters versus non-texters? What's the only way that this difference variable is negative? Is if the texters have a greater response time. So with 90% confidence, I can say that the true difference between texters and non-texters is negative, which implies the response time from texters is higher, which generally when you're driving, that's a bad thing, right? You don't want your response time to be higher, right? So kind of, even with some pretty simple sample data like this, you can make a statement where you could say, texting while driving actually, I guess the way we would say it in English, it slows response times, which means it takes you more seconds, right? A higher number of seconds to respond. Okay. So I have this great meme from the movie Office Space. If you guys haven't watched this, you should look it up. Hilarious movie. But these are the types of statements we can make using these confidence intervals. Okay. So we're going to do this exact same thing. We're going to apply it to Excel. So let's open up that hypothesis testing blank file that we worked off of last class. Now we did all the proportion stuff last class on this South and Midwest file. I now have this male and female worksheets where we're going to look at the difference in sample means between male and female BMI. Right? So go back to this female variable or this variable worksheet and look at this BMI variable. I'm going to calculate the sample mean. So I'm just going to use that average function. Select Control Shift, Command Shift on a Mac, hit the down arrow, then hit Enter. So I've got my sample mean for female BMI. Var.s is our sample variance equation. Just going to select that variable. And then our sample size, we said last class, was just using what? Just the count function. Easy enough. So I've got my sample mean, sample variance, and sample size for female BMI. I then have my other population, right? The male kind of sample data that I had. I'm going to go through and find the average male BMI by just selecting that column. Once again, sample variance is just var.s, and then select that BMI variable. And then my sample size is I use that count function, and I go over and select that BMI variable. Right? So I've got my sample variance, sample mean, sample size for male BMI. I want to put the values I had on the female worksheet over here. So just like last class, I put an equal sign, click on this other worksheet, and then click on the cell that I want to put on the other sheet, hit Enter. Because of the way I had it set up on the other worksheet as well, if I copy down, it stays on that same worksheet and just keeps updating the cell reference so that it just keeps going down and grabbing the next piece of information. Okay. So notice once I have those, this is very similar to how your Excel assignment will work. This degrees of freedom, I already have the equation entered in there. It should automatically kind of update. Okay. So sample mean, sample variance, and sample size for both groups. This equation was already kind of on the file. It'll then round that down or floor that down to the next integer. And now I've got my degrees of freedom. So notice here, I've got pretty large sample sizes. So I should, even finding a pretty small difference between these two groups, right? I'm going to be able to, even like 0.2 or 0.3, that could be a high number of standard deviations because that sample variance being so large, sample size being so large is going to drive down the variance of this difference in sample means. So from here, how do I do my confidence intervals, right? Well, the first thing we need to do is look up these t-values, right? We did this by hand on that texting, non-texting example, where I knew it was the t-value that gives me alpha over 2 on either side of my interval, okay? Now, if I look up just alpha over 2, the way that the equations work in Excel, it always looks at the left side of the distribution. And so I'm going to find the negative value, but I just have to remember that's already built into my confidence interval equation. I just need the absolute value. So if I go to what we did last class, and where was it? Here we are. When we built these confidence intervals for the difference in sample proportions, we were looking up z values, right? So we used that norm.s.inv, and I was using kind of 1 minus alpha over 2. Now, that's because, right, if I want alpha over 2 on this right side, to find the positive value, I would look up 1 minus alpha over 2. Or I could just look up alpha over 2, take the absolute value, and it should give me the same thing. So we can kind of see how that plays out. The only difference is we're not using the standard normal, we're using the student t. So just like I know we did some one population stuff with this, instead of norm.s.inv, I'm going to use the t.inv. Now I can tell it alpha divided by 2, but I forgot to tell it something, right? What did I forget to tell it? Oh yeah, it needs to know what student t distribution to use. So I have to tell it that degrees of freedom, which is no longer 80, right? This was just on the previous example. My degrees of freedom here was calculated for me up in this cell. So click on that degrees of freedom, close my parentheses. Now, I said I also am going to have to make sure I take the absolute value here so that it gives me the positive value. But once I do that, now I've got this student t value. Now, if you had done 1 minus alpha over 2, actually, I have this in the wrong cell, t.inv. I'm just going to show you this for a second. 1 minus alpha over 2, I should get, if I remember to tell it my degrees of freedom, I should get the exact same thing, right? So I could tell alpha over 2, take the absolute value, or 1 minus alpha over 2, and I should get the exact same value. Also notice, if I had used that standard normal distribution, which I shouldn't have been, because my sample size is so large, if we go back, it's been a while now, but I said that student t distribution, as my sample size gets higher and higher, starts to get closer and closer of an approximation to that standard normal. So this with like 6,000 as my degrees of freedom, it's going to be a really close approximation if I use that standard normal. Look, I mean, I'm off at the 3rd decimal, but not by much. Now we're doing this in Excel, so there's no reason to do approximations. It's about the same amount of work to get the exact precise value, but just to kind of reiterate that idea, you can kind of see that play out here. Okay. So we don't need that. I was just going to kind of show you that for reference. Now, when I'm building these different levels of confidence, the only thing that's changing, right, and this is texters, non-texters, ours would be male, female here. But the only thing changing is that alpha at a different level of confidence, which changes that t value. Right? So when I copy this equation down, I want the t value to update. I'm going to use the new alpha, but my degrees of freedom stays the same. So notice if I copy this down and don't freeze anything, I've got some errors. Well, that's because my degrees of freedom is always going to be in that same cell up there. The only thing I want to update is alpha. So now if I froze or I freeze that cell reference, now I should get my 3 t values pretty quickly. Okay. Any questions there? You want to see a cell again? Okay. Now from here, it's really just using Excel to be a calculator. Okay. So I add my margin of error to my lower bound, subtract to get my lower bound, add to get my upper bound. I've got all these values in Excel. It's just going to be a matter of using Excel to be my calculator. Now, I would probably suggest breaking this up into parts. So I'm going to calculate this standard deviation for the difference in sample means in a separate cell. So I'm going to do that. Difference in sample means. So that's going to be the square root of each group's sample variance divided by its sample size. So sample variance over its sample size. Okay. So I've just calculated this, so I've got one number there. So it makes it easier once I go to calculate my upper and lower bound. Okay. So then my lower bound equation, I don't need my parentheses here, but I'm kind of trying to match up with the way I usually write it. I'm going to try to take my sample difference, or the difference between males and females, right? And then I'm going to subtract this t-value, right? Multiply that by the standard deviation for the difference in my sample means, which I had in this cell up here. Okay. So the sample difference, or just the difference in the sample means, subtract the number of standard deviations I want to go, or my t-value, multiplied by that standard deviation for the difference in my sample means, which we had calculated in a separate cell up here. Okay. Any questions over anything there? I'm going to see a cell again. Okay. So if I copy this down, what's the only thing that I want to change? So I need to freeze some of these. What's the only thing I don't need to freeze? Yeah, the only thing that's changing should be the number of standard deviations the way I'm going if I'm looking at different levels of confidence. So everything else other than this t-value reference of K12, I'm going to use F4 or Command T on a Mac and freeze those. Okay. Now, when I copy this down, yeah, I'm using all the same sample information. I'm just going a further number of standard deviations away to get my lower bound. And I've got my three lower bounds relatively quickly. Now, the upper bound equation is the exact same thing. I'm just adding my margin of error. So I said probably the easiest way to do this, you could type it all in again, but I could just copy, hit enter it out of the cell, paste it, go in and change that negative to a positive sign there and add my margin of error. That's all I need to do. Now I can copy this down and I've got my three levels of confidence pretty quickly. Any questions over anything there? You see a cell again? Or... So let's think about what we found here. At the 90% level, right, my confidence interval goes from negative 0.62 to negative 0.11, where my difference that I was looking at was the difference between male and female BMI. So at the 90% confidence level, what can I say about this difference? Well, I can say that it, with 90% confidence, it is a negative value, which the only way that that happens is if the average female BMI is greater than the male BMI. So with 90% confidence, I could say that the average female BMI is greater than that of males. Now, I don't know. I'm not in this field. I know there's issues with the BMI measurement. Maybe here we've uncovered, maybe it's biased towards one gender or something like that. But we can say with 90% confidence that the female BMI average is greater than the male BMI average, right? Or that difference is only negative values. However, notice if I go out to 99% confidence level, well, now I've got mostly negative values, but the true difference could be positive. In fact, it even could be 0. In fact, that would mean they're exactly the same. Right? Can't really say one way or the other. Now, outside of it, like this is kind of the next step of this class, like and more advanced than this class would be. Well, yeah, but the majority of the possible true values for that difference are negative here. So yes, it still could be positive or 0. but the probability that it's negative, it would still be, relatively high, but that's kind of, would be going kind of to the next level, starting to think about those ratios and how we could use those to make statements. But that's the general idea. Okay. Any questions over anything else before we kind of go back to the slides and look at hypothesis testing with this type of problem? Okay. So before we even go to the slides, let me try to fix this first of all. Okay. So I'm going to try to maybe tie some of these things all together. So if we go back to last week, when we're doing hypothesis testing, nothing's really going to be different when we have two population and we're looking at the difference in sample means and we only have sample variances. So it's going to be very similar to what we were doing with the difference in sample means, where let's say, okay, what was this sample difference that I found? Subtract the assumed true difference and then divide by the standard deviation for the difference in those sample means. Now, how do we calculate that? Well, that was just the square root of each group's variance of their sample means, which was the original population variance you sampled from over your sample size, added together. Right. Now, just to kind of make the connection as well, and it was a little bit more complicated, but the test statistic we had for the difference in sample proportions, well, we took the sample difference, which now is the difference in our sample proportions, still subtract the assumed true difference. And here in the denominator, now it's the standard deviation for the difference in our sample proportions, which we said we had a little bit more work to do because we kind of had to find this average proportion between the two samples, but it's still going to be the same relative idea, but we're using an equation that is giving us this standard deviation for the difference in our whatever statistic we're looking at here, proportions. So our test statistical equation, when we have sample means, but we don't know the population variances, we only have sample variances. That test statistic is going to be a t statistic now, right? Because it's going to be coming from a student t distribution. Anytime we only have sample variances, student t distribution. Right? So our test statistic now is going to be the difference in our sample means, or this sample difference we found. So this looks pretty similar to what we were doing before. We're going to subtract this assumed true difference, which once again, on the problems that I give you, what I expect you to do on the exam, I'm always going to be using this assumed true difference of 0. And we still divide by the standard deviation for the difference in our sample means. It's just the notation changes now to kind of represent, we calculated the standard deviation, but we did so using the original sample variances as opposed to known population variances. Okay. So really the only thing different here is notation that just allows us to know like, oh yeah, I'm using population variances here to calculate the standard deviation for the difference in my sample means, so I get to use that standard normal distribution. Down here, I'm only using sample variances to calculate the difference in my sample means, so I have to use the student t distribution. And our degrees of freedom goes back to that nasty equation. So just like with confidence intervals, I'll give you what that degrees of freedom is. Okay. So this is the equation that we're going to use to calculate our test statistic. Other than that, all the steps are exactly the same. We would do this just like we would a one population example where we only had a sample variance, using that student t distribution to look up critical values, p-values, etc. Okay. So let's work through an actual problem here. Scroll ahead. Oh, I had an additional confidence interval. Oops, come on. There you go. Example here. We're not going to work through it in class. I might work through it next week, throwing a batch of questions together that, it's a little bit easier when I'm going through things topic by topic, because like, okay, today we're talking about sample means with only sample variances, and it's a little bit harder to kind of identify when you have what types of problems. So next week, I'll probably have a day where we kind of go through more problems, but it's all various types, and we have to identify what type of problem we have. So we'll save this one for a later date. Or if you want to work through it on your own, you could. Right? It's the same process as what we just did, just different numbers. So if we want to do hypothesis testing, like I said, all the steps are going to be the same, other than this test statistic, which we kind of already talked about, is going to look very similar to what we were doing before, just we're using sample variances. Okay. So let's work through an actual problem. So I've got male and female physicians, and I want to test for whether or not there's a difference in their, was it starting salaries or just salaries, right? So we could do kind of like gender, pay gap stuff here. So I've got a sample mean, a sample variance, and a sample size from each group. But here I just need to identify what's my null alternative hypothesis. Well, if I want to test for whether or not male and female physicians have different starting salaries, and I'm thinking about that difference being male minus female here. If I want to know if they're different from each other, what am I trying to test for? If these two values are different from each other, that's really saying that the difference is going to be any other value other than 0. Right? If they're different from each other, then I'm really saying I want to test to see whether or not that difference is something other than 0. So I would assume the opposite is true, which is that they are exactly equal to each other, that they are not different from each other. Now, another way of thinking about this is if I want to test for whether or not male starting salaries are different than female starting salaries, maybe it's a little bit easier to identify the alternative hypothesis like that, because that's usually how it would be phrased or how we would say it. Well, I know that I need to write out this null alternative hypothesis in terms of the difference. Well, how do I get this difference variable? I'm just going to subtract that female mean from both sides. Now my alternative hypothesis is here, where this just represents that difference variable. And then, okay, I'll assume the opposite is true, which is that this difference is equal to 0. Right? So either way, we get to the same place, but a slightly different way of thinking about that sometimes lines up with the way people think a little bit better. Okay. Any questions on that? How we identified that null alternative? So we saw the word different than. I guess an easy non-technical way to think about what the null alternative were. I told you I'm always going to use assume true differences of 0, right? So we know that we should be having a difference either not equal, less than, greater than 0. And then I said, are they different than? That different than is a key that you're using a not equal to test, just like when we had one population examples. So if I have a not equal to sign the alternative hypothesis, what type of tail test do I have? Evidence on either side goes against the null, so I've got a two-tailed test. Right? So the first thing that we could do is find our critical values. Right? And I can't remember the next question. I believe the alpha is 0.01, but we'll double check that here in a second. So what I want is this t value, or my critical values, that give me alpha total in my tails. Well, for a two-tailed test, I'm going to have two tails. So I'm going to have two critical values, or a pair of critical values, and half of alpha is in each tail. So it's going to be very similar, almost like confidence intervals, right? So 0.01 over 2, 0.005. And I think that, I don't know if I mentioned this earlier, but I said we had to calculate the degrees of freedom. It's not simply n-2. What actually ends up being true is if you have the same sample size, it does end up becoming just n-2. So I would have what? 41 from each group minus 2. I should get this degrees of freedom of 80. Now, I won't ever make you calculate that. What I would do is something like here, or once we have the null alternative, I'm giving you that assumed true degrees of freedom of 80, right? That delta, that equation we had should give us 80. Now, right away, which of these critical values can I rule out if I have a two-tailed test? Yeah, right. I know I have a pair of critical values, so I can rule C out. From there, it's just a matter of, I know that I wanted 0.005 in each tail, and my degrees of freedom was 80. Right? So I'm going to go to that student T table. I want a 0.005 in that tail, all the way down at my degrees of freedom of 80, 2.639. So I've got negative and positive 2.639. And my rejection region is kind of being the area, like, drawing arrows into the tail there. I don't know why I think I underlined something here. This is positive, right? Sorry. Any questions there? So hopefully you're kind of seeing this as a very similar process. It's just a little bit of tweaks here and there, depending on the type of example that we're looking at. So I've got my rejection region set up. The probably easiest way to do this is find my test statistic, plot it against my critical values, and see if it's in that rejection region. Okay? So we're going to have to use our test statistic equation, but we've been given all this information. Like, we have the assumed true difference of 0. We have the sample means, variances, and sizes. It's just a matter of getting our values plugged in and doing the computation. Now, like other examples, I might suggest, maybe you calculate this ahead of time to make, do it in steps to make the likelihood of making a calculator error kind of go down. But you could do it all at one time. So that's what we're going to do. Is we've got our critical values. We'll just plug in all these values we had been given from the problem, the two sample means, the sample variance, and the sample sizes. And we get a test statistic of 29.2 or 22.92. Sorry. So, hopefully at this point, we're starting to get familiar with some of these values. Remember, these test statistics, whether they come from a standard normal or a student t-distribution, represent the number of standard deviations away you are from this assumed true difference value. So being 3 or 4 is usually pretty far. That's a pretty large test statistic. Here, I'm 22.9 standard deviations away. So I'm going to be like way, way out here in this tail, right? This 22.9, this test statistic is easily in my rejection region here, right? So in my rejection region, so I can reject. Let me see, I'm gonna go up here. Now, if I didn't draw out the visual, I can also remember that this equation will give me my rejection decision, which is if the absolute value of my test statistic is greater than the absolute value of my critical value, or this threshold number of standard deviations away cutoff I set, my sample evidence was an even further number of standard deviations away. So here, 2.639, is that less than 22.92? It sure is. So I can pretty easily reject here at the 99% confidence level, right? Alpha we started out with originally was 0.01. Okay. Any questions there? We keep moving. Okay. Let me get a drink here real quick. So, made the rejection decision using the critical value approach, but what if we had wanted to do the p-value approach? Right? Well, we're going to be kind of limited when we're just physically using the tables. So if I think about this test statistic of 22.92, my p-value would be the probability I saw something as far away from that assumed true difference as I did, or anything even further. But remember, with a two-tailed test, it would have been equally as likely for me to see something as far away on the other side. And those also go against the null for a two-tailed test. So I can find the area in this tail, but I then need to multiply it by 2 to get my total p-value. So our degrees of freedom is still 80, right? That was given to us. I need to look up at the degrees of freedom 80, this test statistic. Now, the problem is if I do this using the physical table, at degrees of freedom of 80, it stops at 2.6. I need to go out to 22.92. So I can't actually find the exact p-value. However, if I know that the area to the right of what? 2.639, if that area is, sorry, I was talking, not thinking about what I was doing. The area to the right of 2.639 is 0.005. What's going to be true about the area to the right of 22.9? It's going to have to be smaller, right? So all I can really say here is the area in this tail is less than 0.005. But I have another tail that all I can say is that the area is less than 0.005. So if I wanted to put this p-value in a range, if I know this tail is less than 0.005, I know the total p-value is less than 2 times that, or less than 0.01. So I can still make my rejection decisions, because if my p-value is less than 0.01, well, then it's going to be less than my alphas of 0.01, 0.05, and 0.1. Right? But all I could do is put it in a range. Now, I'll show you this in a second. In Excel, we don't have to just put it in a range, right? On the exam or something, if I had a problem like this, I think on the Connect homeworks, they make you put them in the range, so you get a little bit of comfort looking at these p-values. But on the exam, I would give you like something where the test statistic works out to be exactly one of the values on that table. So you can actually find an exact p-value as opposed to just having to put it in a range. Does that make sense? Questions on that? So not only though can I say it's less than 0.01, what's probably true about this area? Yeah, it's less than 0.005, but it's probably going to be insanely close to 0, right? I mean, the area to the right of 2.6 is 0.005. By the time I get out to 22.9, that area in my tail is going to be so small, right? So this p-value is just insanely 0. It's very unlikely what we assume to be true, that difference is equal to 0. It's very unlikely that it, in fact, is true given the sample evidence that we saw. Okay? And it makes sense if we go back to the original numbers. I mean, I found a difference of what? 33,000 in these starting salaries. So that's pretty strong sample evidence that the difference isn't in fact 0, right? So this makes sense that we would be able to reject with such a high level. So we found our test statistic, we found a critical value. I even added some stuff in with the p-values, just to make sure that we rounded out that example. I didn't mean to do that. I meant to do exit. And then we're going to go back to Excel to kind of end class today. Okay. So if I scroll down here, I've got this set up, and I will change this to 0 because we're going to use that assumed true difference of 0. I'm going to show you how to do test statistics and look up p-values here. So for my test statistic, it's really just going to be a matter of using Excel to be my calculator, right? So I've got, here's my test statistic equation. I'm going to take the difference in my sample means. Let's see if I scroll this over here. So I'm going to take the difference in my sample mean. So male sample mean minus the female sample mean. I'm going to subtract this assumed true difference of 0. Next class, we'll kind of play around. I'll show you another example where we don't have to make that 0, even though I'm going to for you guys. I just want to show you that like you can test against other values, and it makes a little bit more sense in this context. I'm then going to divide by the square root of each group's sample variance over my sample size. Well, here's a nice little shortcut, because if I've already built confidence intervals and I'm doing hypothesis testing for the same problem, well, what did I find earlier? That standard deviation for the difference in my sample means. I don't have to type all this in again. I calculated this up here in the cell, right? It was the same thing that I was using. And this is a different example. It's texters versus non-texters, but it's the same thing I was using in my confidence interval. that standard deviation for the difference in my sample means. So I can just go back up and reuse that value, right? That's all I have to do. That should give me my test statistic. Now I could type all this out, right? Square root, and then go up and select the sample variance from group 1, which was males over the sample size, etc. But since I already had that calculated in a separate cell, I'm just going to click on that cell. Okay. There we go. So I've got my test statistic. If I wanted to find the p-value, well, remember, so here's my test statistic, negative 2.36. I can find the area to the left, but I got a two-tailed test, so I equally as likely to see evidence on the other side that went against the null. So I can find this and then multiply it by 2. If we go back to how do we do that from last class with sample proportion examples, well, that was using that norm.s.dist function. Well, I'm not using the standard normal distribution anymore, but I am using the student t, so I can just use that t.dist. I can tell it, here's my test statistic, comma, here's my degrees of freedom, comma, find the area to the left, right? Or make it cumulative. We always put comma 1 in there. Once I have the area in this left tail, my total p-value is not times 22, but that times 2. Okay. So this should give me my p-value, right? It's the same thing we were doing last class. It's just that I use my test statistic, and instead of looking it up on the standard normal distribution, I look it up on the student t. Okay. Any questions on that? Okay. So we'll hit enter. And I've got my p-value, right? So we'll finish this example up in the next class, kind of doing rejection decisions. But I want to show you one more thing you can do and kind of remind, I've shown this to you before, but I want to remind you of something. Oops. What's going on there? If you have a two-tailed test, you can use this t.dist.2t, tell it your test statistic, comma, tell it your degrees of freedom, and it should give you the same value. The only issue is what? Do you remember what I said for the one population examples? If you use that .2t, for whatever reason, the way that they have it coded up, this function only accepts positive values, which is fine because the area to the left of negative 2.36 is the same as the area to the right of positive 2.36. So the only other thing that I need to do here is I have to give it the absolute value of my test statistic, right? Because it only accepts positive values. But however, now should give me the exact same thing that I found before. Okay. Any questions before we get out of here today? So you've got that Connect and Excel assignment, right? To kind of start chipping away at. You should be able to make a pretty good way through most of them. We'll finish up this example on Monday. Once we do, I'll post the version of this Excel that we did in class. The completed version is already up there. It's going to look very similar, but I've added a couple little things in here and there that might look a little bit different. So I want to make sure that you have kind of both of those. Okay. All right. Have a fun, safe weekend, and I will see you guys on Monday.